In this lab video, I'm going to be talking about the electrochemistry experiment, part 2. As a reminder for part 2, we are looking at electrolytic cells, which are non-spontaneous. So if it's electrolytic, it's non-spontaneous. Non-spontaneous E naught of the cell is negative. And that's why in the video you saw we were applying a voltage to make the reaction go. And a reminder from the previous chapter, delta G of the reaction if it's spontaneous. If it's non-spontaneous, it's positive. So opposite in sign. What's really interesting here for electrolytic cells, you're applying a voltage, so now we have the possibility of water reacting. We'll go over that. So first of all, just a couple of reminders. Anode, I know I'm losing electrons, which is oxidation. Cathode, gaining electrons, which is reduction. In cell 2, which is the example I'm showing you, Ki aqueous. So in my beaker, I've got potassium cation, iodide anion, and water. For electrolysis of aqueous solutions, water is always a possible reaction. So for every single cell in part 2, you're going to write out your possible anode reaction for water, which is the oxidation of water, which is 2H2O, forming O2 gas, plus 4 electrons, plus 4 H plus, and this E for of this oxidation, and this is at a pH of 7. This is not the standard value from your table. This is at pH of 7, which is negative 0.41 volts. Okay, so for every single anode, you're going to write down that possible water reaction. For every single cathode, where we're having reduction, we write down 2H2O plus 2 electrons forms H2 gas. So if you observe bubbles at the cathode, that's the production of hydrogen gas, plus 2 hydroxide ions. So if you had phenolphthalein, you would see that solution turn pink. And the E at pH 7 for the cathode is equal to, I wrote these backwards, so the E ox is negative 0.82 volts, and the E for the reduction at the cathode is negative 0.41 volts. So we always consider water at the anode being oxidized with an E ox at pH 7 of negative 0.82. At the cathode, we have the reduction of water, so water gaining electrons with a reduction value of negative 0.41. So write these down for every single cell. Now we need to think about what ion could possibly react. Here's a hint. At the anode, we typically have anions reacting because anions tend to lose electrons. At the cathode, we typically have cations reacting because cations tend to gain. So the anode, we have our I minus, and the cathode, we have K plus. I know the half reactions, we're always forming the elemental form of the ion, which is I2. We're going to balance this. I see that I have 2 iodines on the right-hand side. Oops. 2 iodine atoms on the right, 1 on the left. I'm going to balance the atoms with a coefficient of 2. I now see on the left-hand side I have negative 2. On the right-hand side I have 0, which means I need to add 2 electrons to the right-hand side, which does indeed match up with oxidation. And the E naught, so now we're back at standard conditions for this, for the oxidation of iodine. We're going to look at our table. And I see right here that iodine as a reduction, so the opposite direction of what we write down is positive 0.54. So remember these are reduction values. So the oxidation is going to be negative 0.54. Reverse a reaction, you change the sign. Okay. And now we have to decide which reaction will occur. So at the anode, we have two possible reactions. The reaction that occur is whichever is easiest to occur. And we can say the reaction with the most positive E-ox will occur. So most positive or least negative, two ways to think about it. And so I'm comparing negative 0.82 to negative 0.54. So there we go. I minus is the reaction that will occur. Now we're going to do the same thing for potassium. Potassium is going to form the elemental form, which is K solid. Got one K on both sides, so that's balanced. Plus 1 on the left, 0 on the right. I need them to be the same, so I add 1 electron because electrons come in as negative. Plus 1 and negative 1 gives me 0. They're balanced. And now I need to find my E naught reduction, because this is a reduction reaction. Go back to the table. And it's a reduction table, so the direction will be the same. And let's look for the potassium, and that's down here. Potassium gains 1 electron to form a solid, negative 2.92 for the E reduction value. Okay. And now we have to decide which is going to occur. Will water be reduced or will potassium be reduced? And we think about the same thing. The reaction with the most positive or least negative, two ways of thinking about that. E reduction is the reaction that will occur. And so the reaction that will occur in this case, we're comparing negative 0.41 to negative 2.92. And so in this case, water is the reaction that will occur. And when you observe this video, you should indeed see at the anode the oxidation of iodide, so probably like a red liquid forming. And at the cathode, you should see bubbles forming and a solution turn pink. The last thing we have to look at now is our overall balanced chemical reaction. To do that, we add up the two reactions that we circled. Remember, electrons must cancel. I can see I have 2 electrons on the right, 2 electrons on the left. They do indeed cancel, so I do not have to multiply my two reactions by anything. The overall reaction then is 2I minus plus 2H2O liquid goes to I2 plus H2 gas plus 2 hydroxide aqueous, and our I2 was indeed aqueous. You saw it dissolving in that liquid. You can go ahead and you can double check. I have a negative 2 charge on the left, 2 negative 1, so a negative 2 charge on the right, and the atoms are also balanced on both sides, so that is the overall balanced equation.